The last speaker of today's sessions is Virgínia Rodrigues from Universidade Federal do Rio Grande do Sul, and she's talking about radar permutations with cycles of the same length. Please, Virgínia.
First of all, good afternoon, everybody. I decided to speak in English, but I don't speak English very often. So I already apologize if the words don't come to my mind, but I hope they do. And I also like to thank the organizers for this opportunity. This is joint work with Juliane Capaverde. She is my colleague at the Federal University of Rio Grande do Sul, and Ariane Massuda. Ariane works at CUNY University in New York. She was a PhD student of Daniel Panario. I should say I was a bit scared when I saw that I would speak right after Daniel, because, when there's somebody that's like a leadership in the field, it's always scary. But I'm very happy to be here. And yesterday, someone mentioned that Fernando Torres liked to get people together and to introduce people to each other. So I decided to start telling you a little bit how we created this girls group, how we three got together, and how we started studying ready permutations. So it all started in Oaxaca, Mexico in 2001 in the conference Finite Fields and Its Applications, number 6. At that time, I was taking my PhD under the supervision of Chuhong Gao. He was a friend of Daniel. And there I met Ariane, she and Daniel Panario. Ariane was about to start her PhD with Daniel. And then 15 years later, Daniel and Lucia Moura, and they were organizing this nice workshop in Florianopolis. I was already at that time working in spectral graph theory. So I was not working at that time in finite fields, but I decided to go and meet Danielle, meet Ariane. She told me she was going to be there. And then Juliane was new in the department, and she also was there. And Danielle gave a nice talk. And after his talk, we decided there that we would start studying something together. And then we studied this very nice paper by Claudio and Danielle on Redi functions. In these papers, they describe the functional graph associated to a Redi permutation. That's the topic, and we use their results for this work that I'm presenting today. And as a consequence, in this little bit of history, continuing that as a consequence, so today I'm going to present the results that we published in this paper, that the same title of this talk, it was published last year. And then we also are, I should say it's going to appear soon because it's almost ready. And in their paper, they propose a problem of studying when two Redi permutations have isomorphic graphs. And then we have now a complete description of that, and depending on if A is not, the field element is or not a square. So these meetings, sometimes they have these nice consequences that people get together and then they start working on some problems. So it's very nice to have the opportunity of participating here of this meeting, of this tribute to Fernando Torres. Okay, to start, I start with some definitions. Earlier today, Fabio already talked about functional graphs, and then so maybe I don't need to, I will skip this slide. I'm going to the example just to show what's a functional graph. I want to get to Redi permutations, so we start with the functional graph of a function over a finite set. So here I have an example. The function takes x to x cubed. It's a function on the finite fields of 11 elements. So the functional graph associated to this function h is you can see here. So we have the nodes or vertices of this graph are labeled by the field elements, and we have a directed edge from 2 to 8 because the function takes 2 to 8. And we have this lace connecting 0 to itself because 0 is a fixed point. So examining this functional graph, we see that there are 3 fixed points and 2 cycles of length 4. And this functional graph consists only of cycles. We can say that the fixed point is a cycle of length 1. So this functional graph consists only of cycles because actually this is a bijection. We say that this polynomial h is a permutation polynomial. So this is, whenever we have a permutation polynomial, the functional graph associated over a finite set consists only of cycles. Here is some motivation why we are going to study permutations. Permutations over finite fields, they are important in cryptography, coding theory, because we can take, people can take advantage on that they are easy, sometimes easy to implement and don't require too much space. And the 2 properties of permutations that we are interested are the cycle decomposition, which means the number of cycles in the graph, the size of the cycles, the number of fixed points. And we are interested in that because those are related to properties of codes and cryptographic schemes. So there are nice applications. So that motivate this study. So we want to get to Reday permutations. So here I recall what's the definition of a Reday function. This is a classical definition, but there are several equivalent ways to define a Reday function. So we consider a finite field of other characteristic with Q elements, with infinity. Yeah, we denote this by P1 of FQ, and then we expand x plus square root of y to the n. And then the Reday function. So if you fix a natural number n and an element in the field, the Reday function, Rna is defined by the quotient of these 2 polynomials into variables that we obtain in that expansion. So it's the quotient of those polynomials if the denominator, when we replace y by a, is non-zero, and also if x is not infinite, otherwise the image of x is infinity. So a Reday function is a rational function. And here just so that we see how they look like, the Reday functions, we listed some of the Reday functions for n from 1 to 5. Here a can be an element in the field. So if we take a different element in the field, we have, for the same a, another element in the field, we have a different Reday function. So you want to get Reday permutations. A Reday permutation is a Reday function that is a bijection. And there is a well-known result that characterizes when a Reday function induces a permutation. So it induces a permutation if and only if Rna induces a permutation if and only if the GCD between n and q minus chi of a is 1. Chi of a is the quadratic character of a. So whenever this GCD is 1, and then we have a Reday permutation. For our work, we used some results from that paper of Daniel and Kuresh that I mentioned earlier, where they describe the functional graph associated to a Reday permutation. So essentially what they say is here, the cycle structure of a Reday permutation. When we say cycle structure, this is the same as saying the functional graph. Since it's a permutation, the functional graph consists of cycles and fixed points. And or if we consider a fixed point as a cycle of length 1, we can say it consists of cycles. And they showed that when we have a ready permutation, the size, how are the size of the cycles and how many of them? So for each divisor of Q minus chi of A, we have cycles of size, the order of n modulo D. And the number of the cycles are phi of D divided by the order of n modulo D, where phi is the Euler's Tauchin function. So the size of the cycles are the order of n modulo D for each divisor D of Q minus chi of A, and this quotient are here phi of D divided by the order are the number of cycles. And we also have chi of A plus 1 cycles of length 1. So they gave the structure of the functional graph, and they also gave the number of fixed points of a ready permutation. So it's GCD between n minus 1 and chi Q minus chi of A plus 1 plus chi of A. Later, we'll call this GCD number D, an integer D. So in the slides that will come, you'll see that I'll talk about the number of fixed points. They are D plus 1 plus chi of A. D always means the GCD between n minus 1 and Q minus chi of A. So one thing that we can notice by the cycle structure described by Kuresh and Panario is that it doesn't depend on the field element A. So if we fix n, the integer n, and we consider two different field elements, let's say A and B, if we look to the ready permutation R and A and the ready permutation R and B, if A and B have the same quadratic character, they will have the same cycle structure. So the cycle structure does not depend on the field element, only on the quadratic character of the element we use to construct the function and n. Here is more motivation. Now, these are some motivation for studying ready permutations. I didn't insert here the references, but they are in the paper. There are some papers here from Daniel, Panari with other people, and some other papers, but I thought it would be too many to mention, too many references, so I apologize for that, but I decided just to, that, you know, if people are interested, I can show at the end the references. So we study ready permutations that decompose into cycles of the same length. Why this is important? Well, people say that we can use them to construct interleavers for turbo codes for people in the area of coding theory. They are interesting for that. And we also saw there were other characterizations of permutations with cycles of the same length. We mean by that all the cycles have the same length except a plus fixed points. So they were given some characterizations for monomial permutations, Dixon polynomials, also for Rayleigh functions and Möbius functions and linear maps. And another application that called our attention is that when the cycles all have length 2, the non-trivial cycles, so we have fixed points and all the other cycles have length 2, these permutations are called involutions. They are their own inverses, and these are good for applications, especially those applications when they don't have much memory and they have to start to store the inverse and the permutation in memory. So it's good to use involutions. So I think we had plenty of motivation for the things we investigated. And here is one of the results. Actually, this is a consequence of one more general theorem that we have in the paper. When we apply that general theorem, that theorem, it uses, we have a system that involves the cyclotomic polynomial. When we apply that for a prime P, we got, I think this is a nice result. where we characterize all integers d such that there is a ready permutation that decomposes into d plus 1 plus chi fixed points and p cycles, whenever p is an odd prime. We call those integers admissible integers. So if we fix an odd prime, we can look at the proper divisors of q minus chi, and depending on their factorization, we can tell if this divisor is admissible or not. If it means that if there is a permutation, ready permutation, that decomposes into fixed points and cycles of length p exclusively, and has d plus 1 plus chi fixed points. So it's very easy to check that. It only depends on the factorization of the divisor. From that result, we got this another nice result, I think, that we can tell when there exists a ready permutation. Fix a prime, I can tell you there is a ready permutation with 1 and p cycles or not. So it all depends on the factorization of q minus 1 or q plus 1. We need to know if it has a prime factor that is a multiple of p plus 1 or a prime factor that is divisible by p squared. So there's also a simple, I think, a simple way to contest if there is a ready permutation with 1 and p cycles for any odd prime p. From those results, we also did some counting. So if we have an odd prime, we can determine the number which we call MD, that's the number of ready permutation with d plus 1 plus chi fixed points, p cycles, and a fixed parameter a. So if we fix the odd prime and the admissible d, so we know there are ready permutations with d plus 1 plus chi fixed point, we can count how many there are. So it is also simple to check. We can count how many there are with that number of fixed points. We also could count how many, the total number of ready permutations, so if we fix the odd prime and we fix an element in the field with quadratic character chi, we can count how many ready permutations there are with cycles of length 1 and p. So it's also very simple to check. I didn't list here because I wouldn't have time, and I believe everybody may be tired at the end of the afternoon. So I just listed here some results that we also obtained concerning involutions. For involutions, we also could characterize all q chi2 admissible integers. So we know when there is a ready permutation that is an involution and has d plus 1 plus chi fixed points. We also did the same counting, the number of ready involutions with a certain number of fixed points, the total, and also the total number of ready involutions. And for involutions, we also could give an explicit formula for n, such that Rna is an involution with a prescribed number of fixed points. So we can say exactly which are the ready involutions with a prescribed number of fixed points. So these formulas are, I think, really nice. And here is another results we obtained. We decided to study involutions with few fixed points. The smallest number of, the two smaller numbers of fixed points that a ready function can have is 2 or 4. So we could obtain which are the ready involutions with exactly 2 fixed points. So we say here with n, and a can be any element in the field with that quadratic character. So we only have involutions with 2 fixed points when a has quadratic character -1. And we also have involutions with 4 fixed points for both characters. And we say exactly the values of n. They all depend, of course, in the field, which field we are interested in. So we know which are the involutions with 2 and 4 fixed points. And some more work we did. We could use the results we got for involutions, and we could, the same work we did for permutations with 1 and p cycles, where p is an odd prime number, and 1 and 2 cycles, we could do the same for 1 and 4 cycles. And so we can characterize how are these permutations, when they exist, and when already permutation has this kind of decomposition and a certain number of fixed points, we also could count them. And I think something that's nice, more practical maybe, we gave in our paper procedures to construct radial permutation with a prescribed number of fixed points and J cycles for J3, 4, or 5. So we can say the steps one should follow if we want to get radial permutations with a certain number of fixed points and a small number of cycles. Cycles of a small length. The length would have to be the 3, 4, or 5. So to illustrate what we can get with our results, there are more examples in the paper. Here I show all radial permutations that have 1 and J cycles. Decompose into 1 and J cycles. Their functional graph has only fixed points or J cycles, where J is 4 or a prime number. These examples over P1 of the finite field with 125 elements. And this table I show when we consider an element in the field A with quadratic character 1. But we also could do the same for A with quadratic character -1. So here, if you look at the table, we have J is equal to, so we are looking at involutions, radial permutations with 1 and 2 cycles. And then if you look in the column of N, so we see here we have N, it can be 123 or 61 or 63. So there are 3 involutions in this field. And for each of them, for example, when N is 61, we see that this involution has 6 fixed points and 62 cycles. We also can see that there are no radial permutations in this field with 3 or 4, with cycles of length 3 or 4, and those that decompose into cycles of length 1 or 5, we see there are 4 of them. These are the values of N for those. So those are permutations R and A. These are the values of N. And A can be an element in the field with quadratic character 1. I didn't keep track of time, but that's what I had. I don't know if it was too fast. I actually forgot to check time. Thank you for